Hi there, guys. I'm about to do the next exercise on from K, so 14J. One thing I forgot to mention in 14K is that they came up with the not degrees of freedom, the critical value in the question. Let's have a look. When did they say it? They came up with the critical value here. Here we go. The critical value for this test was 9.488. Now, these critical values are the same regardless, they come from the same table regardless of whether you're using a goodness of fit test or a test for independence. So if we have a look at this, that 9.488 came from 4 degrees of freedom and testing at a 5% significance level. So this was just a normal chi-squared critical values table, which we're taking it from. Now, you don't need to deal with that in this course, but it's good to be aware of the fact that it's pretty straightforward to find out. And of course, you could use that for coursework purposes as well. Okay, right, so let's look at the next one. So the next one is all about a goodness of fit test again, but this time for the Poisson distribution and the binomial distribution. This is fairly straightforward. It's basically the same thing as what we did last time round. We're just using a different distribution to match this thing too. Okay, so let's go straight into the questions. So we're seeing in this case, let's look at this one. What have we got here? And it says flaws in a length of material, so faults in length of material are thought to be modeled by a Poisson distribution with a mean of 2 flaws per meter. 50 1-meter lengths of material are inspected and the number of flaws in each are recorded in the table below. Okay, so we're expecting these to follow a Poisson distribution in this case. So they're saying if X belongs to this Poisson distribution of mean 2, find X is equal to 0, probability X is equal to 0, and so on. And then hence work out the expected values. So that's really straightforward, really. This is a discrete distribution, so we can simply say, go to Scratchpad, and we can say, well, what's the probability of getting X is 0? So let's go probability, 5 distributions, Poisson, which is Poisson PDF, which is J on my calculator on the TI Inspire, and the lambda, or alpha, or mean, if you like, whichever one you want to go with, but it's calling it lambda on the calculator, is 2 in this case. And then the X value here I'm interested in is 0. I'm going to press OK, and I'm getting out Poisson PDF 20 as 0.135. Okay, and I can see that that's right. I've got my answers hidden over here as well. So yeah, that's right for the first one. And then, of course, we can do that for the other ones as well. There's not too many calculations here. I would not make a table of values for this because you can do this via a table. I think I'll show you that in a bit. But I'm basically just going to control and copy that and then control paste that thing again. And instead of putting in 0, I'm going to put in 1. That gives me my second value in that case. Okay, so I'm doing 2, 0, 2, 1, and so on. Okay, so again, I can do a control paste, still got the same thing saved. And there's my third answer is there. And so the only issue I have is for the last answer, for 4 or greater, I need to do Poisson CDF. So I'll need to go back to do probability again. So menu, probability, distributions, and I'll need to do Poisson CDF. So lambda is 2, lower bound is 4, upper bound is 9,999. And my answer there is 0.41428. So they go 0.143 in the table there. Okay, so that's all good. And then to find your expected values is exactly the same as before. So you'll now times your total in the sample, so 50 by each of those probabilities. So that's super simple. Then write down the null and alternative hypotheses. So we're saying either that the original distribution is being followed or it's not. Now, previously, when it was with the normal distribution, we're saying it's following a normal distribution with a mean of whatever and a standard deviation of whatever. And in this case, we only have one parameter here. So we're saying that this follows a Poisson distribution with a mean of 2 floors per meter. That's the null hypothesis. The alternative hypothesis is that it doesn't follow that. We don't know what distribution it follows. Maybe it's still a Poisson distribution, we don't know, but it's simply, it does follow this, or it doesn't. Okay, so then part D says find the p-value. So now we're going to need to put all of these things into a table. So I'm going to go to home on my calculator, and I'm going to go to spreadsheets, and I'm going to put in my information. So I'm going to put in 5, 10, 18. So again, all I need is an observed column and an expected values column as well. So 11 and 6. And let's have a little look. What did we get for these? Let's just zoom in on these. So I've got 6.77. Again, I'm going to go with the answers here to 3 significant figures. But if I was writing this down during an exam, I'd try and have a few more significant figures there, in fact. So 13.5, 13.5, 9.02, and 7.15. Okay, so there's my table. Now, none of those values are below 5, so we're good to go ahead with this. The degrees of freedom here are 4, so we've got 5 rows, take away 1. So that's 4, so I'm going to go menu, statistics, stats tests, and 7, so chi-squared goodness of fit test. The observed list is in A, the expected list is in B, and the degrees of freedom here are 4. Press OK on this, and I'm getting a chi-squared value of 3.489, which they don't ask for, and I'm getting a p-value of 0.47943 something or other. So here we go, we're getting exactly what they're saying here as well. Okay, so p-value is 0.479. Okay, now obviously at a 5% level, that p-value is not underneath 5%, so therefore we cannot reject the null hypothesis. Okay, so this result is not significant, so no reason to reject H0. So fine. Okay, there we go, question done. Pretty straightforward. Let's have a look at how the book does it though, because I think, let's just check this one out. And let's open this one up. Okay, so yeah, they do something slightly different here. They come up with the values for the, don't want that to happen. Okay, they come up with the values in the table, the Poisson values. Okay, that's interesting. They've used more than 3 significant figures, in fact, because they've used the table values here. So they've used the Poisson distribution in the table itself. So how have they done that? So they've renamed this column X. They've had to come up with 0, 1, 2, 3 anyway. Then they're putting in the next column. What are they saying? They're saying in the cell below, type and press menu, statistics, distribution. So just go to a blank square and then go statistics, distributions, Poisson PDF, enter 2 as mu and X as the upper bound. Okay, X is the upper bound in this case. Click OK. So then we're getting these values here. So that's Poisson PDF, and X is the upper bound. Strange that they call it the upper bound there, not just the particular value that we're looking to find the probability of. And yeah, they've put in X, but you could likewise put in A with some square brackets there as well. So that's going to give you your Poisson PDF. You've still got an issue there though, because you also need your other probability of getting 4 or more. So I think you're going to need to go back to Scratchpad for that. Let's have a little look. Yeah, and then they've done some working out in column C by saying your this is just too slow. I wouldn't do this. This is 50 times by B1, 50 times by B2, and that's super slow. You can do that quicker using your old GCSE calculator. Okay, and you should write these things down in your book, on your exam paper anyway, your calculations. Okay, so there we go. They've written these down. They've come up with the fourth one, no doubt, from going back to Scratchpad. Maybe they've done the alternative, of course, is to find the fourth probability value by simply doing 1, subtract all of the other probability values. Anyway, I don't think that method is quicker. It is possible to do the whole thing on spreadsheets, but I don't think it's quicker. Okay, right. So let's look at the next one then. So the next one is a binomial version of this question as well. So I've got this one here too. So let's look at what they're saying here. So they've got, in a trial of 3 coins, 3 coins are tossed. Okay, find the probability of obtaining 0 heads, exactly 1 head, exactly 2 heads, and exactly 3 heads. And so they're saying in a trial. So in an experiment, there will be many trials. So in fact, the experiment is for this trial to happen 200 times. So Hagar tosses 3 coins 200 times and makes a note of the number of heads each time. Her results are as follows. So here are the results. Now, obviously, you'd expect 0 heads an eighth of the time. That's a half times a half times a half. And 3 heads, same, an eighth of the time. And then the rest of your probability split equally between 1 and 2 heads. Or in other words, the 3 different ways of getting heads, tails, tails. So 1 heads and 2 tails. So heads, tails, tails. Tails, heads, tails, 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 heads. 3 ways, each of which have got a half times a half times a half. Guys, that's pretty simple. If you want to use the binomial distribution to get that, you can, but otherwise it's just there's just a tree diagram, right? So that's just, your heads, tails 3 times over. And of course, I'm missing the other ones here as well. Okay, in a tree diagram in this case. Okay, so there you go. There's your probabilities. You can say, if you want to, that x is binomially distributed with n is equal to 3, because there's three flips of a coin. Okay, and so each one of these trials is a binomial distribution, follows a binomial distribution, but there are 200 times of that thing being carried out as well in the experiment. So 3 and then 0.5. So that's n and that's p on your binomial distribution. So we could work out our probabilities by then doing that on the calculator, but in fact it's simpler than that. Okay, right. So then those are the results. So use the probabilities. There we go. Binomial 3, 0.5, and the fact that Hagar tosses the coins 200 times to find the expected values of the number of heads. So super simple. We then times our probabilities. So an eighth, 3 eighths, 3 eighths, and 1 eighth by 200 to get an eighth of 200, which is 25, and so on. So now we can put in these observed values, the frequencies against the expected values, into our calculator. There are no values there which you can see which are under 5. So the expected values are all above 5. So that's good for us to go ahead with the goodness of fit test. And again, it's very straightforward, this question. So on your calculator, let's go new document, add lists and spreadsheets. I'm putting in 28, putting in 67, 83, and 22, and then the other values, which are 25, 75, 75, and 25. I'll do my tests, so statistics, stats tests, goodness of fit test, which is 7 on here. So observed list is A, and then B is my expected list. My degrees of freedom is 3, so that's 4 take away 1. Answers in C. So there we go. We've got chi-squared value of 2.426, 2.43, yeah, rounded off to 3 significant figures. And the p-value is here 0.48868. So there we go, 0.489 to 3 significant figures. So there we go. We are done with this question, essentially. They're giving us the critical value. Critical value is 7.815. We're doing it to the 5% significance level, so let's just check that one out with the tables. It's 5% significance, and degrees of freedom are 3, so 7.815 there. So we can get that from a table if we needed to. And write down the null and alternative hypotheses. What do they say? They say that the number of heads has this binomial distribution. The number of heads does not have this binomial distribution. Find chi-squared and the p-value. That's just reading from your calculator. State the conclusion for this test. Well, 2 ways of doing it. You can either say that your chi-squared value is beneath the critical value, or you can say that your p-value is above 5%. Both of those, yet again, mean that there's no reason to reject the null hypothesis. Okay, well, there we go. That exercise is done. Or rather, you need to get some practice on that now. My bit is over there. And let's just flick on, see what's coming after this. So we're estimating parameters for the next one. So in this case, we might be talking about the lengths of fish in a lake being thought to be normally distributed. But if that's the case, then we'll need to estimate the mean and estimate the standard deviation, which ultimately should be using a t distribution. Okay, well, that's the next exercise anyway. We'll come on to that in the next video. Thanks for listening.